it's a real privilege to give these talks. I want to thank the organizers for inviting me. I'm going to talk about this subject and some work with Matt Stover on it. To introduce it, I'd like to go back to a very classical problem. Let's see if I can get this here. Wrong way. Okay. So let me talk about the Pell equation, which is one of the first equations you see in algebraic number theory class. You're trying to solve x squared minus dy squared equals 1 in positive integers x and y for some given square-free integer d. If you go on the web and enter in Archimedes plus cattle in Google, you'll find Archimedes cattle problem, which is actually trying to find a solution to Pell's equation, in which the minimal solution, in the sense of the smallest x, is incredibly large. So the number of cows on this island was supposed to be really, really big. And that actually is one of the most important questions about the Pell equation. What is, first of all, it has infinitely many solutions, that's known, but how large is the smallest one, the one with the minimal x of d? So if you think about the number of digits in the x of d, that's more or less the log. And log of little d is the number of digits in little d. So the input to the problem is giving the integer little d, and the length of the input is the logarithm of d. That's how many digits you need to send. And the question is, how big is the minimal solution in compared to the input? And it's to give you an idea about how little we really can say about this. It's not known whether the output, which would be the digits of x of d, is bounded by a polynomial in the input. It's not known if that's a polynomial time problem. Conceivably, it could be. Of course, we don't actually expect it to be. And I'll talk about why in a minute. And that's how I'm going to get into S arithmetic groups and unit groups. So what actually is expected to happen is that there's infinitely many square-free integers d that are positive, so that the logarithm of the minimal solution is at least d to the 1/2 minus epsilon, which is a lot bigger than a power of log. But if anyone could prove that there's no polynomial in log that can bound log of x of d, then that's a field level result. That shows you how little we can do at the moment. So really, another way to look at this is the Pell equation. Is it polynomial time to produce the output in the input? It's unknown, but probably not. So let me continue and do the connection of this to sizes of units. So here's how the Pell equation is related to units, which is also well known from algebraic number theory classes. So if you look at a solution to the Pell equation and you take the x and y that come up, x plus y squared of d is a unit in the real quadratic field, q squared of d. We know what the units look like in a real quadratic field. They're generated by a single fundamental unit, which is greater than 1, together with plus or minus 1. So, in fact, the minimal solution to the Pell equation is some power of that fundamental unit. A nice exercise is check that the power is 1, 2, 3, or 6. And they all happen. So, the Brouwer-Siegel theorem tells you that if you look at this real quadratic field, q squared of d, well, morally speaking, the class number of the field, which is h sub little k times its regulator, is on the order of the discriminant to the half. That's the easy way to say it. The more tricky way to say it is that if you look at fields of a given degree, say 2, then the ratio of the logarithm of class number times regulator divided by log of discriminant to half tends to 1 as the discriminant goes to infinity. The discriminant of the field is more or less d, up to a factor of 4. So in this situation, the regulator of the field, the regulator of this real quadratic field is just the logarithm of the fundamental unit. That's bigger than 1. So what this Brouwer-Siegel is telling us is that the class number times the log of the fundamental unit is on the order to the discriminant to the half. So if you believe the Gauss conjecture that the class number is 1 for a positive proportion of real quadratic fields, then you have 1 times log of epsilon being discriminant to the half on the order of that. And that's where the expectation comes from, that the Pell equation has a minimal solution whose logarithm is on the order of the discriminant to the half for infinitely many little d's, namely the ones where the class number of the corresponding real quadratic field is 1. Of course, we're very far from proving a Gauss conjecture. There's a lot of numerical evidence. You know exactly what proportion you should, of K there should be with this class number 1. The Cohen-Leinster heuristics predict a lot more about how these class numbers should behave. But now, at the moment, all that's known, as far as all that I know, is that there is a constant bigger than 0. Push this up a little bit. There is some constant bigger than 0, so there's infinitely many positive square free integers d. So the log of the fundamental unit is at least that power of the log of the discriminant. And there's some arguments about what's this best C. A little bit of controversy in the literature, but that seems to be what people can do. So the moral here is that at least in the general case, when you have class number 1 in a real quadratic field, the log of the fundamental unit is on the order of the discriminant to the half. So the fundamental unit itself should be something like exponential of discriminant to the half. It's growing exponentially, fractional power of discriminant. It's much bigger than any power of the discriminant. The fundamental unit is bigger than powers of the discriminant. Okay. So now I want to talk about some extensions of this from real quadratic fields to arbitrary fields, and some surprising discovery of Hendrik Lenstra in the 1990s. The moral of the first part here is that units are big. Units in number fields are big in compared to the discriminant. And that will set up what I want to say about Lenstra's discovery. Okay, so we've been talking about the units of number fields. K is my number field. O sub k is the integers. OK star is the unit group. And the question is, how do you measure how big an element of the field is? And the standard method is the height. Okay? So the height function says if I take an alpha that's in the field, well, I look at all the places of the field. That's capital V. For every place, there's a normalized absolute value, which is vertical bar sub V. And I take the product over all V's of the maximum of those absolute values. So just to recall a few things from algebraic number theory, the places fit into 2 types. You've got Archimedean places and non-Archimedean places. And if you're at a non-Archimedean place, it corresponds to a prime ideal of the ring of integers. And the absolute value of the alpha at a non-Archimedean place is telling you how divisible that alpha is by the prime ideal associated to the V. In particular, if alpha is integral at a finite place, then its absolute value is less than or equal to 1. And that product there, the term is just a 1. So to be more concrete, if I take my real quadratic field, which is what I was talking about before, and you take a fundamental unit, epsilon k, the epsilon k is integral at every finite place. Its absolute value is, in fact, 1 at every finite place. So in that product, all the finite places just contribute a 1. And there's 2 infinite places in this case, and at one of them, the absolute value of the fundamental unit will be it itself. At the other one, the absolute value is the inverse of epsilon k. So then you just get a factor of 1 from that. So it turns out that the height of the fundamental unit is just the fundamental unit itself. If I insist I take fundamental units that are bigger than 1. Okay, so the height measures how large this element of k is. And the question is now, if I look at the unit group of an arbitrary number field, and I suppose it's infinite, can I generate it by elements of small height? When can you generate the units groups by elements of small height? But small should be measured in terms of the discriminant. So in the real quadratic case, we knew that the fundamental unit itself, at least for infinitely many real quadratic fields, was expected to be on the order of e to the discriminant to the half. Okay? So it's growing bigger than any polynomial in the discriminant. The height of the fundamental unit, we don't expect that to be bounded by any polynomial in the discriminant. And you can extend that statement from real quadratic fields to more general fields in a sort of naive way. This is what you would expect. Okay. So if you let, I'm trying to be a little careful in saying what you expect. When you look at an infinite set of fields, infinite set of number fields, which have a fixed degree in infinite unit groups, there shouldn't be some polynomial, so that in all of those fields you can find a set of generators, all of which have height less than that polynomial in the discriminant. You don't expect to be able to generate unit groups uniformly over fields of a given degree with infinite unit groups by elements that have heights that are bounded by some power. That's just too good to be true, certainly from the point of view of real quadratic fields. So now I can talk about this surprising discovery of Lenstra, which has always been one of my favorite results. Okay, so Lenstra's discovery, well, it was published in the 1990s. I don't know when he thought of it. That if instead of looking at unit groups, you look at S unit groups, which amounts to saying you allow some primes to occur in the denominators of the elements, then you can find generators for groups of S units that have small height, where the heights of the generators are bounded by a very small polynomial in the discriminant. So this is really surprising. You know, I always found this kind of a miracle. If you go through the usual proof that unit group of a number field is finitely generated, the proof is incredibly inefficient. I mean, it uses Minkowski's theorem multiple times, and at a certain step, it's becoming wildly inefficient. And basically, what Lenstra realized or discovered was that if you deal with S units for moderately large S, the proof becomes extremely efficient, extremely inefficient at producing S units. Fails at producing units, you have to do all kinds of tricks. But for S units, it's really great. And so now I want to try to at least state what his theorem is about units. And basically, the game is that just as the units and the S units are the points of the general multiplicative group over the integers, or the S integers, you can now try to replace the multiplicative group by any old algebraic group and try to prove some phenomenon like this happens. So let me talk about what Lenstra did. Okay, so we need a little more lingo. I have to take some finite set of places, and I'm going to always assume that my finite set of places contains the Archimedean places. So once you do that, you can look at the S integers. Those are just everything that's integral outside of S. So this is just saying that you take numbers in the field so that if you look at the fractional ideal they generate, anything in the denominator is coming from finite places in S. And then you can look at the unit group of that ring. The unit group will be a nice finitely generated abelian group. The rank of the unit group is the number of finite places in S plus the number of complex places minus 1. So this is a nice finitely generated abelian group. When S is just the infinite places, it's just a unit group. Now, you need some measure of how large. We need to measure how big the primes are, the finite places are that you're putting into this set S. If you're going to talk about S units, certainly the maximum of the norms of the finite places in S is going to intervene in how big you have to make a set of generators. So the norm of a finite place is just the size of the residue field of the prime ideal that's associated with that place. So, this over here. So my heuristic statement was that there's a small, that you can generate S units once the S is big enough by small elements. So let me talk about what this really says. Now, in terms of the discriminant, which is also d sub k, and because this is about ramification, the discriminant measures ramification. Suppose that you take an S that contains all the finite places whose norms are bounded by the discriminant to the half times some little fudge factor that's actually less than 1. That's related to 2 over pi to the number of complex places. So you put into S all of these finite places with pretty small norms. But that's not too big a set. Then what Leinster proved was that when you look at the S units, they're generated by elements that have height bounded by a certain fudge factor to the R2 times the square root of the absolute value of the discriminant times the maximum size of a finite place you put it in. So what's really surprising about this is that when we dealt with units, instead of discriminant to the half, there was the exponential of discriminant to the half. So this is a fantastic improvement. I guess what else I want to say here. If you think about the height in this case, the logarithm of the height will measure how many digits there are when you try to write down this unit. So if the height is bounded by this product, you take the log of the height, you get a linear combination of logs of the discriminant and logs of the maximum log. The log of the discriminant is how long it takes you to write down the discriminant. So you've got something that's, in terms of logs, it's linear. It's not just polynomial, it's linear in log of the discriminant and log of the maximum norm in S. And you don't have to put very big places in S either. Okay, so one nice consequence of this was that if you go back and think about the problem of actually producing the unit group, this algorithm of Leinster actually produces a very efficient way of finding the units themselves, not just the S units. I mean, the algorithm for the S units is, we know that we've got generators that are small height. We just go out and look through all the numbers in the field that have that height. That's a finite set. We can find it pretty quickly. But then the issue is, how do you get back from the S units back to the units? And the obvious thing to try to do is to look at the exact sequence that says, if I take an S unit, I can look at its valuations at the finite places in S. The kernel of the map that sends the S units to the sum of copies of Z for the places, finite places, the kernel of that is the unit group. So because of Leinster, we have an efficient way to find generators for this group. And then we have a nice finitely generated abelian group, and we're trying to efficiently find the kernel of that map. But that's where you can use linear algebra to do that quickly. And Leinster had an algorithm that used something that was polynomial and the discriminant to the half plus epsilon. Well, actually, in fact, I think that polynomial can be taken to be degree 1. I wrote polynomial time, but Schoof improved this. So there actually is an algorithm now for generating the unit group in time bounded by this discriminant to the half plus epsilon. And that is the expected length of time it takes to write down the answers. So that's a good algorithm. The heights are big, but you still have something that's quite efficient for generating the unit group. Okay, so the situation for units and S units is really very encouraging. And when Matt was visiting Penn, we started wondering about other algebraic groups, because unit groups are just points of the general multiplicative group. So the groups that are simplest and the closest to being unit groups have come from division algebra. So I'm grateful that Julia has now taught us all about division algebra, so I could take all of that and run with it. So here's the program I want to talk about for the rest of the hour. We'll look at the S units of division algebras. So because of Julia's talk, I don't have to say much about what a finite dimensional division algebra over number field with center the number field is. You know what those look like. And inside such a division algebra, well, you can think about the Hamilton-Quaternion algebras over Q. The Hamilton-Quaternion algebra over Q is a great example. Now, inside there, you'd like to take an OK finally generated module for the ring of integers of the number field, which is an algebra over O sub k, and which contains some basis for B over k. That's an OK order in B. So in Julia's talk, she took the integral Hamilton-Quaternions, and that's what you can think of as D. And then you can talk about the S integers of D by just tensoring that thing with the S integers of the setting. And that contains a unit group. And it's that unit group that we're interested in. So the stupid example of all of this is where you take B to be K itself. If B is K itself, then we just end up with the S units. But now, the kind of thing we're talking about is, for example, the Hamilton-Quaternions over the integers. The Hamilton-Quaternions over Q, K is Q, D is the integral Hamilton-Quaternions. Then you allow some denominators in the coefficients of 1, I, j, and k. And you look at the units. And that's what this kind of group is. So the question is, can we show that once S is large enough, and not too large, you can generate this kind of group, the S units of the order, by elements of small height. Now, the first question is, what do you mean by the height? I mean, back in the case of a number field, we had a very nice way of writing down the height of an element as a product for all the places. So we need some, let's just talk about what you need to do in order to try to make sense of this. You first want to talk about an intrinsic height for elements of a division algebra with center K. And this is kind of nice. I mean, there is a natural intrinsic height on these division algebras. The next ingredient in trying to show that things are generated by elements of small height is to define what you mean by the discriminant of an order. Remember back in the unit and the S unit case, you were always measuring whether things were big by comparing their heights to the discriminant of the ring of integers. But in this case, in this world, the role of the ring of integers is played by this D. So we need to talk about what the discriminant of D is. And there's a natural definition, natural way to do that. And then we want to try to see if we can generalize List as a result. Namely, once the S is moderately large, there's small generators for this group of S units of the order D. Now, one question is, why bother? I mean, this is interesting that you can extend this to division algebras, but you know, it's kind of nice. But why? What is the application? I mean, what's the significance of this? And let me talk about one thing which Matt will discuss further, and also which I think will be the focus of the project for our group this week. It's a nice, another explicit question. Here's an application. The application is to look for presentations of this group of units. So this is an infinite non-commutative group, but it is finitely generated. There's work by Grunwald and collaborators that gave algorithms, but they weren't primitive recursive algorithms. This method is a primitive recursive algorithm for finding generators. And once you find a presentation for these groups, then you can use that presentation to study this congruent subgroup problem. Let me tell you what the congruent subgroup problem is, which is quite open for these groups in general. If you take a finite index subgroup inside this group of S units, you'd like to know, is it a congruence group? Does it contain a congruent subgroup? And what I mean by a congruent subgroup would be, you fix some, say, rational integer m, and then you look at everything in the unit group that's congruent to 1 mod m. So this is an example of a congruent subgroup. And the congruent subgroup problem has to do with asking, does every finite index subgroup contain a congruent subgroup? Now, there are many interesting arithmetic groups for which that's not true. Like if you take SL2 of the ring of integers, not every finite index subgroup contains a cardinal subgroup. Matt will talk about some of the general results. But in the case of these kind of S-unit groups in orders, it's not known either way. So one application of this kind of work with Lindstra's method is it really is very effective in producing presentations for these groups. Now, once you have a presentation, you can start finding all of the finite index normal subgroups that have a given prescribed quotient. And then if you come up with such a quotient that couldn't possibly come from a Congress group, we can classify which finite quotients can come from Congress groups, then you've proved that the Congress subgroup problem has a negative answer. And one of the goals of our little project this week is to try to carry this out for some interesting new case. And conceivably, the result could be surprising or could be expected. We just don't know. Let me just mention the other longer-term problem with this. If you look at the multiplicative group of this division algebra, well, the multiplicative group acts by left multiplication on the algebra itself. So the algebra itself is a finite dimensional vector space over the rationals, so some large dimension. And so left multiplication by an element of V star is an automorphism of this large dimensional space over Q. That gives an embedding of V star into a big GLN over K or over Q, if you like. And in fact, it defines an algebraic group. You can write down equations in the coordinates that are specified by how B acts on itself on the left. So the multiplicative group of B defines an algebraic group, and these rings like D sub S star, these rings of S units, are nothing other than the points that they're more or less up to finite index stuff. They're the points of this group over rings of S integers. So the general question would be, for which algebraic groups, that is, subgroups of GLN over K, defined by some number of equations, for which of these algebraic groups is it true that once S is large enough, the points of the group over the S integers can be generated by elements of small height. So you can come up with different notions of height and try to see if that principle actually applies. And what's interesting about this is that the division algebras turn out to be much more tractable than such things as the matrix algebra itself. The matrix algebra, arbitrary matrix algebras, we don't know if this is true. For G equals GLN, we do not know if this is true. And I'll try to explain why the division algebras are more tractable in this strange way. Well, now I need to do some work to define what heights mean. So the goal here is to talk about what's the intrinsic height, what's the right notion of height on a division algebra over numbers. Okay, so thanks to Julia, we know about Wedderburn's theorem and how to look at the completions of these division algebras. So if I take a place of K, K sub V means the completion of K at the place V. And if I complete the algebra this, I get some matrix algebra over a central simple division algebra over K sub V. For example, if V were an Archimedean place and K sub V were the reals, then the central division algebras over the reals are either the reals themselves, the complex numbers, or Hamilton quaternions. So we know that this central division algebra, its dimension over K sub V is a square, and there's a relationship between the size of the matrices you get and the D sub V. Their product has to be the integer whose square is the dimension of the original algebra over K. So the idea is that I want to use these matrix representations with values in central division algebras to come up with a notion of height. And usually you have to come up with local heights first. So let's normalize this description of the completion of the division algebra V so that when you look at my particular choice of order tensored with the local integers of the center, that lies inside the matrix algebra over the unique maximal compact subgroup sorry, the unique maximal compact subring, that should have been subring, of A sub b. So A sub b is their central division algebra at a finite place. I want to make sure that I've chosen this matrix representation in a sensible manner so that the local integral stuff goes to local integral stuff. And the key fact here is that if you take a central division algebra over a non-Archimedean local field, there's unique maximal compact subring. Bayes' book on basic number theory has still, I think, one of the best references for all of that background. So given the ability to describe the completions of the division algebra by matrices, well, the idea of coming up with a height is not too tricky. You just say, well, first I need to talk about some notion of height coming from elements of A sub b, and then extend it to matrices over A sub b. Now, one of the things in this theory that's important is the reduced norms. So there's reduced norms on both B sub v and A sub b. And what happens is, if you take either of those algebras and you tensor with the algebraic closure of K sub b, you get a matrix algebra. So when you do that and you take determinants, you get a well-defined norm, which is multiplicative. And so at this point, we can do this. If I take something in the local, in the completion of B at V, and I write it down as a matrix with entries in this division algebra A sub V over K sub B, well, I look at those entries and I ask how big is the maximal one of those? What's the maximal size of a matrix entry? And the maximal size function I'm going to use is the norm, the reduced norm of the given matrix entry, but raised to the 1 over dv power. dv squared was the dimension of A sub b over K sub b. And the reason for that 1 over dv is really that that's what comes out of the Lenstra method. If you're going to try to write down a height for which Lenstra's method can be carried out without too much trouble, it's this one. And the global height, then, is just exactly like the formula before. If you take an element in the division algebra, it defines elements in each completion. And so you take a product over all the places of the maximal size of that element in the local completion. But you have to raise that back to the d sub b power. So you take the dv, put the dv in and take it back. Another way to talk about this is that you take gamma, for each place v, you write it as a matrix whose entries are in a division algebra over the local completion, K sub v, and you look at the maximal reduced norm in v-adic absolute value of those matrix entries. I should say that this height is intrinsic for B, but it doesn't agree with the height when you think of elements of the center being inside B. So it actually differs from the height. It's not compatible with the height on K because of these d sub B factors. But at least it's true that there's only finitely many elements in B that have height less than a given bound. And we can use this now to try to extend Lenstra's theorem. Well, the next thing we needed was a notion of discriminant, because if you're going to talk about things of small height, you need to compare heights to discriminants of something. And here we want to measure a discriminant associated to the order. That script D order. Well, so for V in Archimedean place, this division algebra over the local completion at V has 3 possibilities. There's R, the complex numbers, or the real quaternions. Okay? And on each of these, you have a certain natural Haar measure. On the reals, you take the usual Euclidean one. On the complexes, you take twice that. And on the quaternions, you take 4 times the Euclidean Haar measure with respect to that natural basis 1 ij, 1 ij, comma ij. And that gives you a Haar measure on the Archimedean completion of B. Namely, when you take B and you tensor it with the reals over Q, then you get a product of these matrix algebras over each of those types of A sub B's. We've got a Haar measure on each A sub B. We use the components of matrices. They get a Haar measure on the matrix ring. And then inside this Archimedean completion of the algebra, you've got the lattice giving you this order. And so it makes sense to find the covolume of that lattice. And that's the natural discriminant. So this generalizes the discriminant of the number field. And again, I can put in a plug. It's related to the ramification in the division algebra. So you can calculate this discriminant if you know how the quaternion algebra ramifies and how far this order is from a maximal order. Okay, so now we've got things in place. We've got a notion of intrinsic height on these division algebras. We've got a notion of discriminants of orders. And now I can say what the theorem is about being able to generate things S units of small height. So, well, this is a somewhat qualitative version. Remember, in Lenstra's theorem, the main point was that you could generate S units by elements whose height was bounded by essentially the product of the discriminant of the field to the half times the maximal size of a finite place in S, once the S was big enough. So we're going to do the same thing here. I want to say on the first, there's two functions that depend on the degree of the center over Q and the square root of the dimension of the algebra, so that once S contains all finite places that have norms bounded by this one function times the covolume of D to a power, covolume of D should be thought of as the discriminant, then the S units are generated by elements of height bounded by some function that's independent, that depends only on N and D, times some power of the norm of the maximal norm of a finite place in S, where C2 is a certain power. And then you want to multiply that by the maximum of 1, and the discriminant of the order, the covolume of D is really the discriminant of the order, raised to another exponent. And this method has many moving parts, and depending on how you put the moving parts together, you can get better constants C1, C2, and C3. Let me just mention what numbers we do know exist. If N is the degree of K over Q, you look at the number of Archimedean places where the completion of A sub B is the Hamilton quaternions, and you have some explicit formulas for what C1, C2, and C3 can be. And they're not very large, actually. So what is happening here is that in Lenstra's result, you basically just had the covolume to the first power and the M sub F to the first power. Here we have some slightly different powers. And tuning up the method, well, one could spend a lot of time doing that. But what is also nice about the method is it gives you a way to find generators, and then using some work of Sayre, ways of finding presentations. So let me talk a little bit in my last 10 minutes about the mechanism and the proof. And during the project sessions, we're going to discuss this more, and then what you can do with it using to get presentations. So what's the mechanism? So the overall takeaway in the mechanism is this. I'll tell you the main idea. You can use Minkowski's theorem to produce lots of S units. Minkowski's theorem is not good enough to produce units in one of these orders. Because remember, in Minkowski's theorem, you have a large convex symmetric subset of a big space. You have a lattice inside there. As soon as the volume of this set is bigger than the appropriate power of 2 times the covolume of the lattice, you know there's a non-zero lattice. But because of those fudge factors, when you apply this to try to construct elements of D that are lying in constrained Archimedean sets, you discover you cannot hope to be able to construct units. You're not going to be able to get things that are units. But the fudge factors are not too bad. So instead of getting units, you can construct S units for S, a rather small set. So Minkowski becomes efficient because of the constants in Minkowski. It only becomes efficient once you throw in an S, but you don't have to throw in a big S. So let me talk about the details of how you set this up, which are essential to actually doing some calculations. Here, what I want to do is to define an adelic group on which the D sub S star acts. And then I want to look for a fundamental domain for that action. just in the Minkowski theorem, you look at a lattice inside a big Euclidean space. You're trying to look at fundamental domains for that action and look at convex symmetric sets that have big volume relative to that fundamental domain. We want to do something like that, but adelically. Okay? So here's the machinery you need to set up to do it. For every element of the local completion of the division algebra, you have a notion of its norm. Lots of norms floating around here, but this norm is sort of the biggest norm you could get. You take the reduced norm to the dth power. D squared was the dimension of B over K. And then you take the norm of that down from KV to the rationals, the completion of the rationals. And then you have an infinite norm here, which is the product of all these things. And you have a finite norm as well. Now the infinite and the finite norm will be contained in the edels of the rationals, as long as if you take an x that's a product like this, with all of those x of these not zero. So these are edels of Q, and the group we want to deal with uses the edels of the division algebra. So if I take the division algebra B, I can look at its Archimedean completions, and I can look at its completions at finite places in S, and look at the product of those. Now you make a certain edelic group here, which is just the pairs of Archimedean completion points and finite completion points in S, but where the infinite norm matches up with the finite norm in the appropriate sense. Now the reason you want to do that is that there's a natural map from the S units of the order into this, and it lies in that subgroup because of the product formula. The product formula for the reduced norms of elements of D sub S. So we're going to put D sub S inside the D sub S, and the point is that D sub S acts on the left on this adelic group. We're going to try to find a fundamental domain for that action. Once you find a fundamental domain, then you can use that fundamental domain to find small generators for D sub S. So here's a few more details about what's going on here. What the absolute values on the right side there in the definition of D sub S mean is that you think of these as edels of Q, and you take the norm on the edels. Okay. So here's the idea. For carrying out Lenstra method. The idea is to find a fundamental domain for the left multiplication action of the group of S units on this adelic group. Okay? And I want a fundamental domain that's also compact. Once it's compact, there's a very neat sort of topological group theory method that tells you how to find small generators for the D sub S star. So how do you find a fundamental domain for the left multiplication action of these units on this adelic group? Well, you're going to write down a candidate and then use Minkowski's theorem to prove that it works. So the type of candidate you want to take is first you specify some nice compact subset of the Archimedean points, which is convex and symmetric, and so that it has big volume. And this, by the way, is exactly the constant that you would expect to apply Minkowski's theorem to. Minkowski would say that if you take any Archimedean set like that, there's going to be a non-zero element of D inside it. Okay? That's what Minkowski guarantees. Now you need to choose another constant that measures, once you pick this Archimedean set, how big are the components of elements of it. And that's what the M sub x is doing. It's bounding the size of the components of the Archimedean set X, at least their size in terms of norms. And now I can write down what's going to be the fundamental domain for this action. Okay, so the fundamental domain, I just take the Archimedean component to be in my nice compact set X, capital X, that's convex symmetric in the Archimedean points. And then the adelic part, the beta, that should be a product of elements in the completions at the non-Archimedean places in S. But if you take one such thing, you can make sense of the right D ideal that it generates. Even if beta is an adelic, finite adelic thing, it defines a right D ideal by just taking each of the local components, multiplying the local component of D by it, and taking the intersection of all that with B. So you insist that beta is integral in the sense that it defines a right ideal contained in D, but of small index. So this f sub x is compact in the idyllic sense. The ideals that can come up as beta times D's are bounded, and the Archimedean components are bounded. Okay, so the main proposition that one proves using Minkowski is that as long as the S contains enough finite places, then you do get a set here, f sub x, that contains a fundamental domain. It's big. So a way to think about this is that G sub S, this big idyllic thing, is being tiled by translates of a nice compact set. And we can actually make computations about that f sub x. Okay, now how do you come up with this? How do you prove that any such f sub x is a fundamental domain? Finish this. Just kind of quickly. The idea of the proof is to show via Minkowski that if you take anything in G sub S, you can translate it by something in the global S units to land inside your compact set. And what that amounts to is looking for an element of the S units which lies in a certain lattice and lies in another convex symmetric set. And a miracle that happens here is because I'm multiplying, the lattice is defined by beta, and the convex symmetric set is defined by multiplying f of x by x inverse on the right. Well, those multiplications change volumes by exactly the same factor. So Minkowski is good enough to produce an element that lives in this lattice and in that convex symmetric set. And then you have to do some extra estimates to prove that not only is it an element in the lattice, it's actually an S unit. And those computations are basically showing that whatever fudge factors you had to throw into Minkowski are not so big that you get primes bigger than the primes in S coming into the denominators or numerators of C. And now let me just finish with the last topological lemon. So what have we got here? We've got a fundamental domain for the action of D sub S on G sub S. And this is a really neat topological lemma that I think can be used in lots of different ways. If you have this G sub S, which is an idyllic group, and I have a set of topological generators. Okay, topological generators just means that that set of generators together with any non-empty open generates the group. And it's symmetric so that every element of P, its inverse is also in P. Then the point is that you can take the fundamental domain that we've constructed, look at everything that can be written as a product of something in that fundamental domain, times a topological generator, times something that's the inverse of something in the fundamental domain, and look at everything in D sub S that lies in that can be written that way. And that collection generates D sub S star. So this is a way of saying that if you can construct a compact, nice fundamental domain for an action of a group on some other group, you have a procedure for producing generators for the discrete group that's active. Okay, so I think what the application of this is to proving this height bound is, well, you choose a set of P that are topological generators of small height, and then you bound the heights of the elements of things that lie in that intersection. And that's how you end up proving it. Let me say something about why this is true. Why would you expect to be able to say that your discrete group is generated by its intersection with this nice small subset? And that'll be the last thing I have to say. But it's one of these sort of memes that one can use in lots of different contexts. So the idea is to say, of course, that if you look at the group that's generated by all those elements, that's got to be everything. And the trick is that if you take the group that's generated by those elements, and you take that group and multiply it on the right by elements in the fundamental domain, you end up proving that that set of products is stable under right multiplication by the topological generator. Basically, you can commute any topological generator acting on something in delta times fx. You can commute that topological generator through basically by definition of delta. So there's a little bit of twisting around here with alphabets. But because if I want to take a y that's an f of x multiplied by a tau in p, I know that anything in the group at all can be written as an element in d sub s star times something in the fundamental domain. So when you write it out that way, what you find is that the gamma that comes up in making that computation actually lies not only in d sub s star, but in those triple products. So the gamma is one of your generators for delta. And the bottom line then is that when you do the replacement there, gamma tau times y times tau times equals gamma x, you end up getting that delta times the fundamental domain is stable by right multiplication by the topological generators. But since they're topological generators, then it has to be everything. So now you've shown that delta times the fundamental domain equals g sub s. But if I take f of x to be a fundamental domain for the action of gamma, maybe after shrinking it a little bit, that will force delta to be the whole group d sub s. Once you know that delta is big enough so that all translates of this f of x give you g sub s. So I think probably that would be a good place for me to stop. And next time Matt will continue with this and talk about how you use it.